Good morning, one and all. My name is V. Abhijit Kumar. I am studying in BTech first year, second semester, CSC, AI and ML, that is Computer Science and Engineering, with a specification of Artificial Intelligence and Machine Learning, Institute of Aeronautical Engineering. In this concept video of the subject of DEVC, that is Differential Equations and Vector Calculus, I am going to explain about the topic of the integration on Fourier transform. So let's dive deeper into the topic. So first of all, let's go through the contents which I am going to explain in this PPTX presentation. In the first place, I am going to introduce the topic of Fourier transform, and after that I am going to explain about the importance of Fourier transform in differential equations and vector calculus, and I am going to explain about integration properties of Fourier transform after that, and after that I am going to explain about Fourier transform of derivatives, and I am going to explain about solving partial differential equations or PDEs, whatever we call them, using Fourier transform method after that. And after that, there are a few of practical applications of this concept of Fourier transform. I am going to explain about them. And after that, finally, I am going to conclude the topic of Fourier transform. Now, first of all, let me introduce this concept of Fourier transform. By definition, the concept of Fourier transform deals with decomposing a function into its constituent frequencies. Or in other words, Fourier transform is a mathematical tool used to break a function into sine and cosine waves, which are its frequency components. We do it sometimes because it helps us understand what frequencies are present in a signal or a function. It's like converting a musical signal into its individual notes, or whatever the analogy we related to it, we can understand it more. The formula here, as you can see in the slide, it is capital F of omega is equal to integral of minus infinity to plus infinity of small f of t into e to the power of minus I omega t dt. Here the capital F of w is the transformed function of the f of t, where the f of t, the small f of t, is the original function, the time domain or space domain, whatever we call it. Here t is the time constant or space constant. The omega is angular frequency. The e to the power of minus I omega t is the complex exponential which we use to analyze a lot of frequencies. Here I is the complex number, as we all know. This concept has a few of the key applications: signal processing in audio analysis, radio analysis, and image analysis, solving DEs or solving differential equations, because it transforms hard problems into simpler algebraic ones, and it is implemented in physics too, especially in quantum mechanics and wave analysis. Hence, this is the introduction to Fourier transform. Now, let's talk about the importance of this concept of Fourier transform in the subject of differential equations and vector calculus. It is useful in solving linear PDEs or linear partial differential equations, whatever we call it, because Fourier transform can be useful to turn partial differential equations into easier algebraic functions. This makes solving them much faster and simpler. This works best for linear equations with constant coefficients. And after that, it is used in simplification of convolutions. A convolution in time or space becomes the multiplication in frequency. This greatly reduces the amount of computation needed, and it is very common in systems analysis and signal processing. Hence, this concept of Fourier transform is useful over there too. And after that, application in vector fields and potentials. This concept helps to analyze vector fields by separating frequency components, and it is useful in electromagnetism, fluid flow, potential theory, and all of that. By example, heat and wave equations can be treated as an example. The heat equation describes how temperature spreads, and the wave equation models how vibrations and sound are exist. Hence, Fourier transform provides exact, specific, particular, and efficient solutions to both of heat equation and wave equation, and all of these problems which we can consider to be solved most importantly. Now let's go through the integration properties of Fourier transform. There are three main properties. The first is linearity. As we can see, the formula is f of af of t plus bg of t is equal to af of omega is equal to bg of omega. The Fourier transform is linear in this scenario, which means that if we add two functions, their transforms also add. If you multiply a function by a constant, its transform also scales by the same constant. This makes it very easy to work with combinations of signals. And after that, the next integration property is integral over time. The formula, as we can see, is the integral of minus infinity to infinity f of t dt is equal to capital F of 0, which means that the total area under a function or its integral over all time is directly related to its Fourier transform at frequency 0. This is very useful when analyzing the average or steady state behavior of any signal. And after that, scaling. As we can see, the formula is f of at of omega is equal to 1 by modulus of a into f of omega by a, which means that the stretching or the compressing a signal in time affects its frequency content, because stretching in time compresses the frequency spectrum and compressing in time stretches the frequency spectrum. This helps us in understanding about how speeding up or slowing down a signal changes its frequency characteristics. Hence, these are the integration properties of Fourier transform. Now let's go through the Fourier transform of derivatives. As per the formula, we can already see that f of dn f of t by dt to the power of n is equal to I omega to the power of n of f of w, which means that we can deal this formula towards n number of frequencies, which we can use in a lot of mathematical calculations required. We can use it to convert any differential equation into an algebraic form. This simplifies the concept of solving complex differential equations. Now here the complex differential equations, as we all know, is the differential equation which has the I in it. Hence, this is the explanation of Fourier transform of derivative. Now let's talk about solving partial differential equations using Fourier transform. Here I can explain just three simpler steps. First one, we have to apply Fourier transform, and after that we have to solve the algebraic equation, and after that we have to apply the inverse Fourier transform wherever required. This helps us in solving any given partial differential equation. For example, if we consider heat equation, the heat equation is dou of u by dou of t is equal to alpha dou square u by dou x square. Here, as we all know, if we can apply the formula of Fourier transform, any such kind of equations can be easily solved. Hence, this is the explanation about solving PDEs or partial differential equations using Fourier transform. Now let's talk about practical applications of this concept of Fourier transform. This concept of Fourier transform in general has a lot of applications. I have personally chosen only 4 of them to discuss about right now. The first one is signal processing. We know to process any signals, to amplify any signals, to filter any signals, to achieve the modulation of any signals, we can apply this concept of Fourier transform. And the next one is quantum mechanics. This concept of Fourier transform is applied a lot in quantum mechanics. One of the best aspect is Schrodinger equation. And after that, electrical engineering. The concept of Fourier transform is applied a lot in electrical engineering. One of the best aspects is circuit analysis. And after that, image processing. To amplify any image, to modify any image, to emphasize any image as per its details in JPEG form, or to compress any image, this concept of Fourier transform is applied in the data of the device, in which we apply all of these things to do with an image. Hence, these are the practical applications of this concept of Fourier transform. And finally, let's come to a conclusion. By concluding this topic, we all came to know that Fourier transform is a key method for integration and simplification. This concept enhances the problem solving skills of us in differential equations and vector calculus. This concept is widely used in theory and applications. Hence, this is the conclusion I would like to give for this topic. And finally, I would like to thank the respected professor sincerely for giving me this wonderful opportunity to talk upon this wonderful topic. Thank you.